Hello, everyone. Thank you for attending today's webcast. This is session 4D, Heat Exchanger Components. My name is Kyle Glusenkamp from Oak Ridge National Laboratory, and I'll be the moderator for this session. So we'll start this webcast with a few housekeeping announcements, and then we'll quickly move on to our presentations. First and foremost, thank you to all of our sponsors and ACEEE Ally members for their support of the Hot Water Forum and ACEEE. Secondly, be sure to check out all the tabs on the left-hand side of the app. From there, you can network with attendees and program participants, visit sponsor pages, and engage in our game to possibly win a free registration to the 2023 Hot Water Forum in Mission Hills, California. And the resources section includes the program and a list of attendees for downloading. Lastly, we ask everyone to please help in our planning of future HWFs, Hot Water Forums, by completing the conference evaluation. Anyone who completes the evaluation and includes a testimonial will receive a $25 discount off their 23 Hot Water Forum registration. Unfortunately, because this session is being recorded prior to the start of the HWF, we will not have the opportunity to answer questions live today. However, we encourage you to reach out to the speakers with any questions or information you have to share. They can be reached by messaging them in the Program Participants tab on the left-hand side of your page, or by reaching out to them by email. And the presenters have either shared their email in the slides or they'll include it in the presentation. And now I would like to introduce our distinguished panel of speakers. They are Yoram Shabtai, Gautam Ramchandran, and Stephen Harrison. And we'll start with our first speaker, Yoram. Yoram Shabtai of Heat Transfer Technologies is a 25-year heat exchanger design veteran with a master's degree in heat and mass transfer. Shabtai heads the consulting firm Heat Transfer Technologies, LLC, or HTT, and as a licensed HVAC engineer, provides designs for current and novel condenser and evaporator coils. HTT is also the official technical advisor to the International Copper Association, providing guidance and designs for many types of HVAC and refrigeration systems. Yoram regularly speaks at conferences about new upcoming heat exchanger technologies and related development work, and HTT also works with industry leaders providing prototype heat exchanger service for evaluation. For more information, he'll have his contact information at the end here. And with that, I'll turn it over to you, Yoram.
Thank you, Kyle. I'll go right to the presentation. Hi, everyone. Thank you for joining this presentation on the advantages of small diameter copper tubes in heat pump water heaters and the use of simulation software in its design. Historically, tube diameter in heat exchangers have come down in size from 5/8" OD in the 60s to 5 millimeters today and below. The main drivers for the change are increased system efficiency, regulations requiring reduction in refrigerant charge, for example, using flammable refrigerants, and system cost reduction. Why smaller diameter tubes in heat exchangers? From a refrigerant point of view, the ability to accommodate low quantity of flammable refrigerant, and from a performance point of view, increased heat exchanger efficiency, thus improving system COP, and also heat exchanger size reduction. Two case studies will show the advantages of using small diameter copper tubes in heat exchangers. One is a display cabinet undergoing a refrigerant charge reduction by changing the tubes from 3/8 or 9.52 millimeters to 5 millimeters. The other is a cold climate heat pump water heater using 5 millimeter tubes and R290, which is propane refrigerant. On the right, you can see the amount of room air conditioner units sold in China in 2021, which is quite a high number, 45 millions almost, 44 millions. Simulation software helps design heat exchangers. There are many different types and kinds, and we're going to cover one by International Copper Association. HXSim is such a simulation software that can help design and optimize the evaporator of a heat pump water heater, for example. HXSim is used by many engineers at numerous OEMs. Some of them are on the screen. The software will be reviewed in the next couple of slides. The equations governing heat transfer and mass flow are employed in HXSim software that calculates the performance of tube fin heat exchanger coils to a high degree of accuracy. A wide range of parameters can be varied with ease in the latest generation of the simulation software. Tube diameter from 9.52 to 4 mm outside diameter, various refrigerants, including natural refrigerants, different heat exchanger shapes like L shape and C shape, and various fin types, including slit and louvered fins, are available as shown in the diagram. The process of using HXSim simulation software is mostly as follows. Tube and fin size and types are selected, then the tube connections and circuits are added, and the working parameters like refrigerant and air mass flow rates are entered. The results will provide temperatures, capacity, pressure drops, and other valuable information. The two pictures depicted show an L-shaped heat exchanger on the left with temperature per tubes, and on the right, airflows. Another example of 3D results showing tube temperature gradients using colors. The cold inlet is at 7 degrees C and the outlet is at 25.8 degrees C. The graphical user interface of HXSim allows the selection of tubes and fins common in the industry. The program has built-in correlations from actual tests. You can see on the right the connections on the return bands of the heat exchanger. Those two pictures provide an example of HXSim circuitry in 2D on the left and 3D on the right. The 2D view makes it easy to make the connections between the tubes while building the heat exchanger in the simulation. Once that is done, it can be checked by moving to a 3D view. The next few slides will show two case studies and resulting advantages of using small diameter copper tubes. Case study number 1 is a condenser coil for a display cabinet. The original tube size is 3/8 or 9.52 OD tube. The simulated replacement is a 5 mm OD tube, as shown on the right column. Due to the use of 5 mm tubes, the heat exchanger depth and height, down in the table, are reduced as shown. Row and column spacing is also changed to accommodate the smaller footprint of the smaller tube. This case study also changes the refrigerant to R290 propane, which is an environmentally friendly refrigerant. The images depict the simulation views of the connections in 3D and 2D. On the left is the original design, and there are 32 3/8 tubes, and on the right there are 40 5 mm tubes. The table clearly shows the advantages of using the smaller 5 mm copper tubes. The table on the left shows thermal capacity increased by 6.8% from 762 watts to 814 watts. Weight was reduced by 26%, as seen on the bottom, from 135 grams to 100 grams, the refrigerant weight. And all that in a smaller envelope, as seen on the table on the right. Heat exchanger depth was reduced and the heat exchanger height was reduced. So with 5 mm coils, the capacity is higher refrigerant charge is lower, and the coil envelope is smaller. Case number 2 is a heat pump water heater with 5mm copper tubes and R290, courtesy of Lordan. The fin pattern shows the difference in fins using various tube sizes. Fins for 5 and 7mm tubes are denser, since tube diameter is smaller, but they do not necessarily exert higher pressure drop than larger tubes. The photo shows HX sim results of the cold climate heat pump water heater evaporator in 3D, with temperature distribution across the L-shaped heat exchanger. This is a photo of the actual heat pump water heater evaporators in production at Lordan. There are 2 of them stacked one on top of the other, and note the L shape and hairpins on the side facing up in the photo. This table shows a comparison of the heat pump water heater using 4 different tube sizes. It's very informative. Tubes go from 3/8 down to 5mm OD, and all these simulations are done while keeping the performance fixed at 14.4 kilowatt, as shown on the rightmost column. The results demonstrate that using 5mm copper tube helps reduce heat exchanger weight, reduce refrigerant charge, reduce weight of tubes and reduce weight of fins, reduce heat exchanger envelope or volume, and all these advantages are depicted in green. With 5mm tube, again, for the same capacity, the coil weight is lower, the refrigerant charge is lower, and the envelope is smaller. The takeaways from the 2 case studies are that 5mm copper tube help reduce heat exchanger weight, refrigerant charge, weight of tubes and fins, and heat exchanger envelope. HX Sim simulation software helps design and optimize heat exchangers. This simulation is offered at no charge to qualified engineer, and the ICA has arranged for a process for download, which is described in the slide. There is additional information on smaller diameter copper tube case studies. Heat pumps are included, and a lot additional applications are covered, and all of that can be found at microgroove.net. Just a few words about the possibility of using 5mm copper tubes for CO2 gas coolers. 5mm tubes can be used with CO2 due to their small size, and companies like Lordan do use it for their CO2 applications, as do so many others. Articles about the use of 5mm tubes in CO2 gas coolers can also be found on microgroove.net. Thank you very much, and for any additional information, details are on the right.
Great. Thanks so much, Yoram.
Thank you.
Our next speaker will be Gautam, and he will be presenting on a CFD approach to modeling gas-fired water heaters. So Gautam Ramchandran is from Gamma Technologies. Gautam is currently a senior engineer there, and for the last over 5 years, he has supported the development of GT Suite multi-physics simulation software for modeling various fluid and thermal applications, such as positive displacement machines, bearings, hydraulics, and lubrication systems. Also HVAC and R systems and water heaters. He holds a master's degree in mechanical engineering from Purdue University. And with that, I'll turn it over to you.
Thanks, guys.
Oh, there you are. Okay, good. Yeah, go ahead.
Yep. Thanks, Kyle. Thanks for the kind introduction. Hello, everyone, and welcome to this presentation. My name is Gautam Ramchandran, and I will be presenting on the topic a novel 3D and 1D CFD approach to modeling gas-fired water heaters. So here is a quick outline of my presentation. I'll begin by talking about the motivation for the study and modeling water heaters in general. I will then walk you through the 1D computational fluid dynamics solver approach used by the software GT Suite. The model setup and initial results will be shown, and I will then discuss how 3D CFD could be used to better calibrate the 1D model and provide some updated comparisons to test data. Finally, a few suggestions for future work will also be shown. Water heater designers face several challenges during development. Iterating between designs and physically testing each design can be expensive and time consuming. Determining the optimal design in this fashion can be tedious as well. It is also hard to identify potential problems early in the design process. And this process can also be error prone and sometimes misleading as well. Um, we also are well aware of the capabilities of 3D CFD, which is very useful and a predominantly used tool that can help reduce physical iterations. But these simulations can take a long time to run, especially for transient 24-hour runs, for example, which can take of the order of several hours or several days even. So these are some challenges that multi-physics simulation and 1D CFD can help resolve. GT Suite is the 1D CFD tool chosen to simulate this gas-fired water heater thermal fluid system. The 1D conservation equations, including mass, momentum, and energy, are solved to resolve the physics accurately. A staggered grid approach, as shown over here, is used to discretize the pipes into multiple subvolumes along their lengths. Scalar variables like density, pressure, and temperature are solved at the center of each subvolume, while vector variables like mass flux and velocity are solved at the boundaries between the subvolumes. The robust solver also handles two-phase flows and combustion, which are key physical aspects, especially in the case of gas-fired water heaters. This approach helps resolve the quantities well along the length of the pipe, or in our case, maybe the height of the storage tank. And as you can see from the image over here, the pressure drop is well resolved along the length of these two pipes shown here. Coming to the next physical phenomenon that plays an important role in water heaters, this is buoyancy, which is a physical phenomenon. It's important to take into account, especially with hot water heaters. It plays a strong part in the thermal response and performance of the heater. The images on the right illustrate this well. So when the center plate is separating the hot and the cold waters is removed, the hot water quickly rises to the top. The solver approach in 1D to characterize this is to discretize the tank into many axial subvolumes along its height. And when the temperature in one subvolume is hotter than the volume above it, the heat is then exchanged, allowing the hot water to travel upwards. Similarly, mixing is another important phenomenon that is important to consider. And as shown in these images, comparing a 3D CFD cross-section and the 1D model, water is basically allowed to mix from the dip tube entry to all of the volumes within the tank. The rate of this mixing is controlled via a mixing factor. And this approach was based on the publication referenced over here, both for buoyancy as well as mixing. Coming to the model layout in GT Suite, there are many different circuits interacting with one another as shown here. Shown in blue is the cold water line from which cold water is drawn into the tank. In red is the hot water line where the hot water is sent to the downstream system. In yellow is the air fuel circuit containing the burner, which models combustion. And the water heater storage tank itself consists of various aspects, including the tank and the flue geometries. We'll discuss this in the next slide in a little more detail. Finally, there's a control logic which has been developed to determine the mass flow rates of the air and injected fuel, which then undergo combustion. The water heater storage tank model takes into account various inputs, such as the tank geometry, including the volumes and the drip tube lengths uh, and diameters, the wall layer materials and thicknesses, as well as the geometrical properties of the flue and the heat transfer between the flue wall, the water heater in the tank, and the water and the walls of the tank. As well as allows the specification of thermocouple locations along the tank height to measure the transient temperature response for the water. So highlighted here is a calibration parameter, which we will discuss in the context of this study, and that is the heat transfer multiplier for the heat transfer between the flue gas and the water as a function of the tank height. So in a preliminary run with no calibration performed, you can see the comparison between the test data as well as the 1D CFD run. While the runtime was very fast, taking less than 20 minutes for a 24-hour transient run, the water temperature within the tank was over-predicted with increase in tank height. So especially at the thermocouples 1 and 2, you can see that the temperature is over-predicted compared to test data. So in order to improve the accuracy of the 1D model and take advantage of the runtime savings, a standalone 3D CFD steady state study was run on the flue geometry using GT Converge in order to calibrate the heat transfer from the flue to the water. At the bottom, which is the combustor inlet, a constant mass flow and temperature boundary condition of the burned air fuel mixture was imposed. An ambient pressure boundary was used at the flue outlet near the top. The outer flue wall had the wall temperature imposed as a fixed value, while the baffles within the flue the baffle walls were treated as adiabatic boundaries. A standard K epsilon turbulence model was used with the piezo solver scheme. Shown here are basically cross sections displaying the velocity and temperature distribution along the height of the tank, actually along the height of the flue line. With the results of the 3D steady state CFD run available, the 1D CFD model was then run under identical conditions. As discussed previously, the heat transfer multiplier was varied with the flue height to target the average temperature at the flue inlet, the middle of the flue line, and at the outlet of the flue line. So as you can see, following the calibration process, the steady state temperature values are pretty close to the distribution which was observed from 3D CFD. Following this calibration, the 1D transient model was rerun with the updated heat transfer multiplier versus flue height values. And it was observed that the model predicted temperatures that were much closer to the test, even at the top of the tank, as shown here. This study shows that significant time can be saved by running a steady state 3D CFD model to better calibrate a fast running 1D model instead of attempting this exercise as a full transient 3D CFD study. Some other interesting model predictions and outputs include the total energy consumed as a function of time, the heat loss breakdown, especially the standby losses from various components, in this case, along the sidewall, the top and the bottom of the tank. You can also check out the mean tank temperature and many other outputs like the pressure drop within the tank and so on. Some other metrics that can also be predicted, but were not compared to tests in the study, include the first hour rating, the UEF, and recovery efficiencies as examples. Some suggestions for future work to extend the study include finding the optimal layout and the highest efficiency by varying many of the geometrical inputs like the baffle and the tube design of the exhaust flue, the air-fuel ratios, the water flow rates, insulation parameters for the flue and the wall tank walls, the drip tube location, thermostat locations, as well as the control logic to replicate test as well as run different conditions. There is also the possibility to analyze the equilibrium chemistry and the chemical kinetics in more detail. So determining the reaction equilibriums of the various burnt species concentrations at various pressure and temperature conditions, as well as couple this 1D CFD model to other commercially available 3D CFD codes as well. That concludes my presentation. Thank you for watching, and for more information, feel free to reach out to me. My contact information is provided here, and please check out our website for additional information to model other types of water heaters as well. Thank you.
Great. Thanks so much. So now we will hear from Dr. Stephen Harrison of QSBR Innovations, and he'll be speaking on the backflush technology. So Dr. Stephen Harrison has many years of experience in the development of thermal energy systems for domestic hot water, space heating, and cooling. As a faculty member in the Department of Mechanical and Materials Engineering at Queen's University in Kingston, Ontario, he has taught courses on renewable energy, heat transfer, and thermal systems design. Author of numerous technical papers and patents, as the director of the Solar Calorimetry Laboratory at Queen's, he has supervised applied research projects for industry and government partners. His past experience includes 8 years as a research officer at the National Research Council of Canada, where he was involved in the development of both national and international standards for solar heating equipment. Since that time, he has been Canada's representative to various IEA tasks, ISO, and ASHRAE committees focusing on thermal energy systems. In 1999, he co-founded Enerworks, a leading manufacturer of solar thermal products in North America, and in 2005, he became the theme leader for solar heating and cooling within the Canadian Solar Buildings Research Network. This network included the participation of researchers at 11 universities across Canada, and most recently, he has supported the research and product development activities at QSBR Innovations, focusing on sustainable energy systems. So Dr. Harrison, please go ahead.
Okay, thank you. So my presentation today is intended to introduce passive backflush technology as a means for maintaining the performance of high-performance heat pumps. So we've seen the motivation to improve the efficiency of domestic hot water units, primarily to reduce the fossil fuel consumption. The industry has developed and promoted heat pump water heaters that are compact and efficient. Many of these units were developed with compact brazed plate or coaxial heat exchangers as condensers or desuperheaters. But maintaining the performance of these systems is challenging in regions with hard water conditions that tend to increase the rate of fouling and scaling on heat exchanger surfaces. As a result, some manufacturers have switched to systems with material-intensive custom wraparound condensers that have the potential of performance and cost implications. To complicate things further, there are new requirements to replace current refrigerants with more sustainable alternatives. So hard water conditions exist through much of the US and North America and Europe and around the world. And this can have a significant effect on the performance of heat exchangers and condensers. You know, when we look at what is the cause of fouling and scaling in heat exchangers, we see that calcium carbonate, which is an inverse soluble salt, is present in many locations in the water supply. And if you refer to the graph to the right-hand side of the slide, you'll see a image which shows the decrease in solubility of an inverse soluble salt as the temperature is increased. The net effect of this, as we'll see, is that when hard water comes in contact with hot heat exchanger surfaces, the inverse salt precipitates out and deposits on the heat exchanger surface. So this can affect the performance of the heat exchanger. It restricts the flow through the heat exchanger, increases the pressure drop, and lowers heat transfer rates. As well, this can have an overall effect on the effectiveness of the equipment, resulting in reduced lifespan and potentially higher maintenance costs. So passive backflush, how does it work? It works by backflushing the heat exchanger surfaces with cold water each time water is consumed. This tends to redissolve the salt deposits and also scour the surface, removing the buildup of scaling. The graph below shows an accelerated test, an accelerated fouling test on two identical heat exchangers. The blue line on the bottom shows that the flow rate through the heat exchanger is reduced over the period of the test, while the red curve shows the heat exchanger equipped with PBF and shows that it's relatively unaffected. Both of these heat exchangers were run with the same source of hard water, and both were subjected to the same pressure head. Now, this is an accelerated test, but it's not unlike what you will see in regions with high concentrations of inverse solids. So if we refer to the diagrams or the photos shown to the right-hand side, if we look at the top figure, we see that this is a conventional plate heat exchanger, which is being charged by a hot fluid, and cold mains water is being drawn from the bottom of a domestic hot water tank and circulated through the heat exchanger in a counter flow configuration. During a hot water draw, the PBF valve, which is located at the heat exchanger, reverses the flow direction and causes cold mains water to be pushed through the heat exchanger to the bottom of the tank. So, in effect, backflushing the heat exchanger refers to the reversal of the flow direction in the heat exchanger as hot water is consumed. And this can be applied to brazed plate, clamp plate, coaxial heat exchangers, and condensers. The reason that it is passive is that it's not required for the home or business owner to activate or initiate this action. In effect, every time hot water is consumed, the heat exchanger is serviced. And I have a little video, short video just showing that on the right-hand side. So passive backflush was developed for indirect solar hot water systems, and it has been installed on thousands of units in North America, which are still operating. And what we see is that we can apply this technology to heat pumps. And what's shown here is a typical heat pump water heater using a compact plate condenser heat exchanger located at the top of the tank. Mains or domestic hot water is circulated through the heat exchanger and returned to the tank. In this case, the backflow valve is located at the top of the heat exchanger, and mains water is directed through the unit during draws of hot water. There are many configurations where this can be used. The right-hand side is what I have just referred to on the previous slide. On the far left, we see a compact heat exchanger located external to the tank using a natural convection flow loop. So there's no pump involved in this, and it delivers hot water to the top of the tank, stratifying the temperature profile. The PBF valve is located on the top of the heat exchanger. You can apply this to pump circulation loops with the pump either located above the heat exchanger or at the inlet to the heat exchanger. The pump can be switched off during the draw process with a thermal or a pressure switch. And another alternative with low pressure head circulators is to actually backflush the pump while it's running or while it's shut off. The other thing to note is that during the hot water draw, the heat exchanger is still transferring heat to the hot water, but the flow configuration is instead of counterflow, it's parallel flow. So there's a changing landscape now, which is the heating industry is facing. In effect, it is requiring the phase down on the use of HFC refrigerants in air conditioning equipment, and a variety of legislation is being put in place to encourage, I'll say encourage, these changes to be made in the near future. And this is happening in North America as well as in Europe and other parts of the world. So a part of this changing landscape is the phase out of these heat transfer refrigerants, and a number of natural refrigerants are being proposed. And this has raised some concern as to the flammability of these refrigerants, and particularly the level of charge that exists in heat pumps. So there are a number of design alternatives that can be considered by the industry. They can use wraparound heat exchangers, which are on the exterior of hot water tanks and tend to be custom fabricated and have special requirements in terms of their placement and insulation. With passive backflush, though, it's possible to use widely manufactured compact heat exchangers and condensers with these units. The impacts of fouling, I've mentioned. There are increased operational costs, increased pumping power required, decreases in heat transfer, performance reductions, and loss over time of stated coefficients of performance. If not dealt with, expensive cleaning procedures and replacement of parts and labor costs may occur, and these may result in warranty claims. So there's a number of applications and benefits, obviously, to this. It can be applied to heat pumps, both geothermal and domestic hot water at the commercial or residential level. Can be applied to tankless water heaters, boilers, solar thermal systems, and district energy systems. The benefits, as I've referred to, are systems performance is maintained, operational life of systems is extended, of hard water in or hard water fouling in regions have these conditions. The system offers this continuous flush and eliminates the need for chemical descaling. And it also enables the use of high performance compact plate heat exchangers that lower material content and cost and minimize refrigerant charge levels. So QSBRI and NeoPerl are collaborating to bring the third generation of this patented technology to the market for use in a variety of systems. The intention is to offer a low-cost unit that's reliable, compact, non-corrosive, and adaptable, and easily configured. PBF is ideal for residential and commercial hardware, natural convection or forced convection applications, and it's possible to integrate in OEM components and systems. So I'd like to thank you for watching my presentation. And if you have further questions or inquiries, please contact Ben Stinson at QSBRI or Frederick Fraze at NeoPerl. And if you have further inquiries, you can refer to our website and look for the latest information on PBF and other technologies. So thank you for your time.
Great. Thanks so much, Stephen.
Okay, you're welcome.
Yeah. And we now have a little bit of time for discussion. Since this session, as a reminder, we're pre-recording this session, so you all are viewing this as a recording. So today our live audience is on the day of recording, our live audience is our presenters. So we'll just have a little bit of an opportunity for the presenters to ask each other questions. Anyone want to get us started?
I have a quick question for Steve. This is Yoram. I was just curious, what is the water usage for one cycle of the water? The BPF, what do you call it, BPF?
Yes. No, thanks for the question. So you have to look at this, I think, in a slightly different way, is that the process that initiates the backflush is the user of hot water actually consuming hot water. So the backflush water is actually delivered to the hot water tank and ultimately is redissolved in the water and ends up going out and is supplied to the end use. So net, there's no additional consumption required. And the fact that this occurs every time hot water is drawn off the storage tank, this happens many times a day as well. Okay, thanks.
Yeah, that's important to know, that there is no downside to the backflush. No additional water usage is important in some areas where water is scarce, for example.
Yes. Yeah.
Or expensive.
We appreciate that.
So that's a plus that is good to know.
Mm-hmm.
Yeah, thanks for that question, Yoram. And just to recap briefly, we started talking about a tool to design heat exchangers using the newer small diameter tubes, and then we moved on to a CFD studies for gas-fired water heaters, and then we finished with the passive backflush technology. So yeah, questions, open to questions on all of those topics. Gautam, were you going to say something?
Yeah, I just had a question for Yoram. That was a very interesting presentation, and I was just wondering if HXSIM is capable of handling transient boundary conditions, and can this HX model be co-simulated with perhaps a full system model containing other components like maybe a water heater and compressors and expansion valves and so on?
Thank you, Gautam. Good question. And for the first part about transient, HXSIM, only transient depiction is the colored temperature depiction on the tube circuits, which the program registers and shows as it goes through the phase change of the refrigerant, and that's time dependent. But there is no variable compressor component that can be added, because HXSIM also does not simulate a whole system. It only simulates the heat exchanger. For a whole system, there are other simulation softwares out there, some free and some you pay for. So HXSIM only does the heat exchanger. You provide parameters, input parameters, and it's an iterative process, and you get the performance. It is very accurate because it was done. The correlation equations were studied using real heat exchangers in wind tunnels and extrapolated. Same with different fin designs. So those, actually, some drop-down menus have components from specific manufacturers, like tubes with a specific rifle geometry internally or any different patterns. So you can select hundreds of different tubes and fins that were actually tested. So as a heat exchanger simulation component, it is very accurate, but it does not do a whole system with compressors, valves, and etc.
Okay.
Thank you.
Thanks.
So I have a follow-up question to my co-presenters. You've both outlined and demonstrated various software for modeling heat exchangers. I'm interested to know the geometry of these heat exchangers, is this input from a CAD file primarily, or can they be generated within the software, as some of the 3D configurations start to get quite complicated? So yeah, maybe Yoram, if you want to
Sure.
go first, and then go with them.
Right. So in HXSim, you actually design the heat exchanger within the program. You have round tubes and plate fins mostly. There is no, I've seen you showed plate type heat exchangers, brazed plate type heat exchangers. HXSim does not do that. It does mostly round tubes and what is called plate fins, so flat fins,
Yes.
and they can have louvers.
Yeah.
So there is a graphic user interface that allows you to do it very quickly and easily.
Mhm.
And you build it yourself based on either available patterns, like the distance between the tubes, or something new that you want to try. And you can also design your own circuitry, how many inputs and the manifold and outputs and where it is on the heat exchanger. But it does not have a CAD input where you can input a drawing of a heat exchanger, even if it's this type, and it will decipher it. The output can be in the form of data in various forms, and graphical interface, and you can print it or save it and so forth.
Okay.
That's how it runs.
Okay. Now, that software is primarily focused on air side evaporators and condensers, is it?
It's refrigerant to air, yes.
Yes. Okay. As opposed to refrigerant to a liquid.
Yes, it's not. There is no liquid component that can replace the air. It's always refrigerant inside the tubes and air outside of the heat exchanger.
Okay. No, that's great. Well, that's a big component of system design. So that's great. Yes. And Gautam, do you want to tell us about your software? You were working in 2D, and then you showed that you had better results in 3D. Was that? It looks like you used a different piece of software for the 3D rendering. Was that generated in CAD first and then imported, or was it possible to do that within the particular software?
Yeah, so the initial part of the study was actually a 1D CFD model for the system. It basically takes in the geometrical parameters of the tank and various other aspects like maybe the flue baffle flue area, uh, various restrictions. So it's very flexible in terms of input. Um, for the 3D CFD, we actually partner with one of our um, partners called Convergent Science. So they develop a software called Converge, which we use Converge as a sort of a preprocessor or in terms of GT Suite to actually populate the inputs to the 3D CFD model. So we have a preprocessor called Gem 3D, which actually takes in CAD of the actual system, the piping, the various tank geometries, and so on, and you can convert it easily using a conversion process into various pipes or bends or splits, valves, and so on, various types of components. So the setup I showed today was actually more of a parametric study that it could be used for, but it can be done from CAD and populated for a ready to run simulation.
Okay. And the cases you showed, were those on the burner side? Were those forced airflow or combustion, or were they a natural convection induced flow?
It was a forced convection study. Yes.
Okay. Well, thank you for that.
Yep.
Well,
thanks for the questions.
Great, thanks. And Steve, I think you might have had to drop off around this time. You're welcome to drop off if you need to.
Yeah, leave. I'll leave. I'm hoping not to drop off anytime.
Well,
All right. So
good call.
yeah, I'm not sure how I exit, but I'll stop sharing my screen. And thank you, everyone, for the interesting presentations and taking the time to listen to mine. Okay. And thank you, Kyle, for.
Thank you, Steve.
Okay.
Thank
Bye
you,
bye.
Steve.
Okay. Bye bye.
Thanks, Steve.
I had maybe one more question for Gautam. I was wondering, in your CFD study of the gas-fired water heater tank, was there anything that was really surprising, or something that for the general water heater people in the audience today, that they might not expect? Could you tell us about what was one finding along those lines?
I think so. The studies that we done, I showcased one study for a particular baffle geometry, but I think it's been interesting to work with different types of geometries, and you can have a very different steady state temperature distribution depending on uh, seemingly minor changes with baffle geometry. So I think that's where 3D CFD could really help, because it helps to better calibrate the heat transfer between the flue to the water, which maybe a 1D model cannot capture as accurately. So that's where this sort of co-simulation study was pretty useful and interesting to work on.
Yeah, that's a good point. Could you give like one example of, what would be a small change that would result in a unexpectedly large difference in the temperature profile?
I think, well, it's very geometry dependent. So it's something, I guess I can't reveal details about geometry because we worked with a commercial customer on this, but essentially anything that would reduce or change the baffle flow area, which would increase or decrease the restriction, I think, and that could be dependent on the number of fins, or even the spacing between the fins and the baffle. Uh, those all played a big role, and it's pretty simple to study those parametric I guess components using GT Suite, um, spacing the areas out and things like that, basically.
Great, thanks. And if I'm not mistaken, I think we might have time for maybe one more question. Yoram, I wanted to ask a kind of similar question to you. Was there something unexpected or counterintuitive that you find as you go to these smaller diameter refrigerant tubes?
Yes, Kyle. One thing to keep in mind is, as you saw in one of the slides, that there are many more tubes when they're smaller versus larger tubes. So the increase in the number of tubes will require planning of the circuits. There will be more parallel circuits in order to prevent an increase in the pressure drop, in the refrigerant pressure drop, as an example. So even though there's a multitude of tubes, you can increase the number of circuits to maintain an acceptable refrigerant drop through the heat exchanger. And that also helps with the efficiency. You do need a distributor that can distribute, instead of maybe 2 circuits, you need 4 or 6, but that's no big change. And that's just something important to keep in mind when designing relatively large heat exchangers in 5mm. Because of so many tubes, you need to increase the number of circuits and paths to stay within a reasonable refrigerant pressure drop. Other than that, the airside pressure drop doesn't actually increase much because the tubes are smaller. The multitude of tubes does not affect it much compared to larger tubes. The patterns, the distance between the tubes is pretty much the same. There are optimization studies that were done, and you can find them in microgroove.net. For example, You may find, just as a rough number, 19 millimeters by 21 millimeters would be a good tube pattern for such fins. And there are studies available that provides these exact numbers for the higher efficiency with the least airside pressure drop penalty, and so forth. So all this information is available. And also how to design heat exchangers when you have multitude of 5 millimeter tubes, you can find available in the microgroove.net. So that's a very helpful place to go, where you can see different case studies, different applications, and it will help you build your own.
Great. Well, I think we can conclude our session here. Thanks so much to our presenters, and thank you to the audience for joining us today. Hope you enjoyed watching, and we'll see you on the next one.
Thank you, Kyle.
Thanks,
Thank
Kyle.
you, Gadam.
Thanks, Yoram.
Thanks. Bye.
Bye-bye.